Yes, in Laplace transform, on the last lecture, just I started inverse Laplace transform. In which I told you that there is no direct method to find the inverse Laplace transform, but we can obtain the inverse Laplace transform by all the formula of Laplace transform like that, because we know that if ft is a function, then Laplace transform of ft is capital Fs. So from here, inverse Laplace transform of Fs is equal to ft. So all the formula can be used to find the inverse Laplace transform, and as I told you, we have the number of formula, we can list the formula of Laplace transform, and by those formula we can obtain the formula and results for inverse Laplace transform, and as well also by the various properties, those can be used as a formula directly, as I told you, can be used for the formula of inverse Laplace transform, like for shifting theorem, change of scale property, Laplace transform of derivative, Laplace transform of integration, Laplace transform of t into ft, Laplace transform of ft upon t, and so on. Right. So up to the last lecture, I discussed these things, how you can obtain the formula for the inverse Laplace transform from the given formula of Laplace transform. Today, first I will take one or two examples. How can you solve the numericals by using these properties for the inverse Laplace transform, and then there is a specific formula for the inverse Laplace transform, that is the convolution theorem, which I will state and prove, because proof is also part of your curriculum. Right now, I will take an example. Find inverse Laplace transform of the following. First part, that is that is 1 upon s square plus a square, and second part, that is s upon s square plus a square whole square. Right? If we take these two examples, right, how we can find the inverse Laplace form. In first part, actually we have to find the inverse Laplace transform of s square a square. Right? If you see this here, it is of type inverse Laplace transform of s upon s. You can put it into this form. So here, Fs equal to 1 upon s square plus s square, and we have a property, that is the Laplace transform of integral. As I discussed, I told you the Laplace transform of integral 0 to t ft dt is Fs upon s. Right? So by this property, we can find inverse Laplace transform of this is equal to integral 0 to t ft dt. So first of all, we have to find the f of t. F of t means we have to find the inverse Laplace transform. We have to find the ft. Right? F of t, small f of t. What is small f of t? That is, small f of t means inverse Laplace transform of capital Fs, that is inverse Laplace transform of 1 upon s square plus a square. That is a very important formula, very useful formula. I have told you that is directly, this is 1 by a sine at, right? This is our f of t. Now, by this formula of Laplace transform, we know that inverse Laplace transform of Fs upon ft and dt. That is the formula obtained from the formula for the Laplace transform of integral. Now you have already obtained ft. Simple put here ft and integrate this. This is a problem of definite integral simply. That is inverse Laplace transform of 1 upon s times s square is integral 0 to t 1 upon a sine at dt. Now calculate this definite integral simply. Then take 1 upon a outside the integral and you do that integration of sine at is minus cos at upon a t to 0. If we take a outside 1 by a square, upper limit cos at, lower limit cos 0 1, that is minus cos at upon a square. That is your required answer. That is your answer of the first part of that question, right? So you see here how we use the formula of Laplace transform to convert for inverse Laplace transform, right? Now similarly, second part of the question we can solve. Second part. In second part we have to find the inverse Laplace transform of s upon s square whole square, right? So here we have to find this. Here if we see that here s upon s square plus y square, number of methods, various methods by which we can find this inverse. But if we take fs is 1 upon s square plus a square, right? If you take this, then from this fs, if you analyze that, if we differentiate this, then what is the derivative of this? This is minus 1 upon s square plus a square whole square 2s, right? So this is minus 2 is common, that is s upon s square plus 4 square, and you have to find this. This is the function for which you have to calculate the inverse Laplace transform, right? d by ds. So by this we know that formula that Laplace transform of t into ft is minus 1 d by ds of fs, right? And this implies that inverse Laplace transform of d by ds of fs is minus t ft. This is the formula converted from the formula of Laplace transform, right? Now by using this formula we have to find the inverse Laplace transform of s square plus a whole square, and that is equal to minus 1 by 2 inverse Laplace transform of fs d by ds of fs. This is, so by this formula this is minus half t ft, and ft can be calculated from here. If you see that, what is this? This is inverse Laplace. ft means inverse Laplace transform of this capital Fs. So inverse Laplace transform is 1 upon a sine at. So substitute the value of this. This is t into ft, and we have to calculate this one, and this is value of inverse Laplace transform t of ft. That means if we divide this, this is t into ft inverse Laplace transform of d by ds of this. This is ft, and ft is this, and this formula is simply that is minus 1 by 2 t ft is equal to 1 upon a sine at by this formula minus, right? And substitute this value because this is, and Laplace transform of this is this. Finally we get this is we have value of this minus 2 inverse Laplace transform of this is TFT. TFT means this is minus half, or TFT means T 1 by A sine AT. Right? This is the formula. Or minus TFT, so minus 1 plus. So finally we get T upon 2A sine AT. This is the answer of second part of that question. Right? So by these two examples, I think you can understand how we use the Laplace transform formula of Laplace transform to find out the values of inverse Laplace transform. Right? These are the examples in which you can very easily understand how can you find the inverse Laplace transform with the help of all the properties of Laplace transform and formula of Laplace transform and standard results of Laplace transform. Right? Now, I will take up one specific formula that is only for inverse Laplace transform. That is a theorem, and this theorem is known as convolution theorem. Convolution theorem, and convolution theorem is important application point of view as well as also proof point of view. First, what is the statement of this theorem? If inverse Laplace transform of Fs is f of t and inverse Laplace transform of Gs of g of t, then by this theorem inverse Laplace transform of Fs into Gs means inverse Laplace transform of product of these two functions is equal to integral 0 to t fu g of t minus u du, or it can be also represented as f, just binary operation with g. This is the statement of convolution theorem. Means if we have to find an expression, inverse Laplace transform of an expression, and we can put that expression into the product of two terms, two functions of S, then we can find Laplace, inverse Laplace transform of their product by the help of convolution theorem S. Now, first of all, I will prove this theorem, and then I will discuss how can use this theorem to solve the numerical question. To prove this theorem, let us assume that function phi t is equal to 0 to t f of u g of t minus u dt du. Take this function as a phi t. If we take phi t this function, then from here you see that two things. Number one, phi dash t is number one. Okay, this is, we take this is a function of t. Now we have to inverse Laplace transform of this. So for this, then we take Laplace transform of phi t, and we prove that Laplace transform of phi t is this capital Fs into Gs. Then inverse Laplace transform of this. And by the first principle, by the main formula, by the basic formula of Laplace transform, what is this? This is 0 to infinity e to power minus t phi t dt. Now, substitute the value of phi t, because phi t you assume this integral, so 0 to infinity e to power minus 2 in bracket value of phi t is 0 to t f of u and g of t minus u du and dt. Right? And if we see that, so this is a double integral 0 to infinity and u equal to 0 to t e to power minus st f of u g of t minus u du dt. Take it as equation number 1. Now this is a double integral. So now we have to solve the double integral. In second semester, I have already studied about the evaluation of double integral. There are a number of principles to evaluate double integral, in which you know that there is a principle that to solve or to evaluate double integral by the help of change of integration. And here we use that concept. Means first we change the order of integration of this double integral and then evaluate very easily, because this is a double integral with respect to u and to t, and here limits of u is 0 to t and t is 0 to infinity. Alright, so by principle, if we solve this directly, that will be a very lengthy method, because you know that there is a evaluation principle for double integral, that is that will depend upon the limits. And there are two types of the limits. One is constant and another is variable. Constant limits mean all the limits are constant. Variable limits means one limit is variable and one limit is constant. Then principle states that if first we integrate with respect to the parameter whose limit is variable, and then with respect to the other parameter. So here, by this, according to this variable u, limits of u is variable, so first we have to integrate with respect to u. If we try directly, that is very lengthy. So first of all, here we change the order of integration and then evaluate this. And how change the order of integration? You know that if first we take the region of integration. What is the region of integration? Region means that is bounded, region bounded by all four limits. What is the limit? T equal to 0 to t equal to infinity, u equal to 0 to u equal to t. These four limits are this. If you draw this, if you take a graph, this is limit t, this is region, this is axis u. If you first limit t equal to 0 means u axis, t equal to infinity means just imagine, we are imagining this is virtual, t tending to infinity, this is the point. U equal to 0 means t axis, u equal to t means this line, like y equal to x line, in x vector you take this. So we have the region of integration here is this, O, A, B, O. Basically, this is the region of integration, right? In which we have to integrate this, we have to change the order of integration. And you know that to change the order of integration, because limits of double integral will depend upon the variation of rectangular small strip. And we can take two types of strip here. One is horizontal strip and there is vertical strip. Then along the strip and along the variation of the strip, values will give you the limits of double integral. So to change the order of integration, first we see that what is the actual position of a strip. So if according to this double integral, if we see that, then actual position of a small strip is vertical. So to change the order of integration, we consider here a strip horizontal PQ in this region. Now, if you see that figure, then PQ varies horizontally from P to Q, and that will give you limits for according to T, limits for T. So at P, T equal to U, and at Q, Q is infinity point, so T equal to infinity. This is one limit, and then see PQ varies vertically from lowest point to highest point. If you see that lowest point, A is the lowest point of the region, that is A, and highest point is B. At A, T axis, U is 0, and at highest point, this is infinity. This is the point of intersection of line U equal to T and T equal to infinity. Now these are two new limits. So after changing the order of integration 1, we get Laplace transform of ft left hand side, right hand side What is the right hand side? Double integral e to power minus st f of u g of t minus u function not change. Here du dt, so now we take dt du, and so limits of t, that is t equal to u to infinity and u equal to 0 to infinity, right? These are new limits, and this is the double integral, which is you denote equation 1 after the change of order integration. And now you have to solve this by the principle of evaluation of double integral. And in principle, you know that if one limit is variable and one limit is constant, then first we integrate with respect to the variable whose limit is variable. So here t is variable and u is constant. So first we integrate with respect to t. So take this integral outside, with respect to t, take fu is outside, and here in integral we are taking t equal to u to infinity, function of t, that is e to power minus st, g of t minus u, and dt, and du take outside. Now first I am going to integrate integration with respect to t, and to integrate this we have to use the substitution method. Put t minus u equal to w, then dt equal to dw. Then limit change, when t equal to u, then w equal to 0, when t equal to infinity, w is also equal to infinity. So by this substitution, this integral becomes then Laplace transform of phi t is equal to integral u equal to 0 to infinity f of u, and in bracket this is w equal to 0 to infinity e to power minus s, in place of t, that is u plus w, and this is g of w and w. This is, and then du. Right, now you can take e to power minus su outside the integral, because the integral is with respect to w, fu, and in bracket you get w equal to 0 to infinity e to power minus sw, g of w, dw, and du. Right, now if you see this term, this expression in bracket, this one, and you know the formula of basic principle of Laplace transform, then what is it? U equal to 0 to infinity e to power minus su fu. So this is the Laplace transform of small g, and that is denoted by capital G of s. And you can take capital G of s outside the integral, and finally we get this one if you take this one into g of s, and again by first principle, what is it? This is the capital Fs, means Laplace transform of small f. Then finally we get Laplace transform of phi t is this. Therefore, inverse Laplace transform of Fs into Gs equal to phi t. Phi t means you assume this integral 0 to t f of u and g of t minus u du, and that is your statement of convolution theorem. That is your required proof. That is the right hand side of the convolution theorem. This is the proof, and proof is also part of your curriculum, so you have to prepare this for examination and as well as your some internal examinations. Right? This is the only one specific formula to find the inverse Laplace transform. Right? Now, I take one example based on the convolution theorem, by which you clear this, how can you use the convolution theorem whenever you have to find the inverse Laplace transform of a product. So we take example. Find inverse Laplace transform by of the following function by convolution theorem. That is, take same example, s upon s square plus 4 square. Take this as an example, right? We have to find the inverse Laplace transform of this. That just some which have already proved this by directly by using property and various formula, and by convolution theorem how it will be solved. Please see solution. We have to find this s upon s square plus a square whole square. Now we can break into the product of two functions. Take first function s square plus a square into 1 upon s square plus a square. Right? So take this one as capital Fs, take this one as capital Gs. So this is thus left hand side of the convolution theorem. We have to find the inverse Laplace transform of capital Fs into capital Gs. So here Fs we are taking s square plus a square, and Gs we take s square plus a square. So by Fs you have to find the Ft. Ft means inverse Laplace transform of Fs. This is directly formula. You know that it is cos At. And from here Gt, that is the inverse Laplace transform of Gs. That is already directly formula. That is 1 upon a sin At. Right? So what is the process? First, you break the given function into the product of two functions. Take one as capital Fs, another as Gs. And from capital Fs, by inverse Laplace transform, you find the small f of t. By capital Gs, again by inverse Laplace transform, you find a small gt. Now, by convolution theorem, you know that by convolution theorem, we know that inverse Laplace transform of Fs into Gs is integral 0 to t f of u g of t minus ut. So therefore inverse Laplace transform of s upon s square upon whole square is integral 0 to t fu. Ft is this, so fu means cos au, and gt minus u, so gt minus u is 1 by a sin a in place of t, that is tu and t. Right? This is just this by convolution theorem. Simply we have already find ft and gt. So from ft gt we will get the function of fu and g of t minus u. Simply now integrate this. You know that this is a type of cos a sin b, and we have the formula 2. If we multiply 2 and divide by 2, then it will become 2 cos a sin b. In class 9 standard in trigonometry, you have this studied this is cos a sin a minus sin a plus b minus sin a minus b. This is the standard formula. So by using this, we multiply and dividing by 2. So this is 0 to t, and 2 cos a sin b means sin a plus b, a is cancel out. Then finally we get sin a t minus sin a minus b. Sin a minus b means au means that is 2 au and minus a t, right? And g of u. This is the simply two functions, difference of two functions. Now you directly integrate them. That is integration. One thing is very important which you have to care. That is integration is with respect to u. So t is independent of u. T is will act as a constant in sign of integration. So here in first term, sin 80 into 1, integration of 1 is u and limit u equal to 0 to t. Here integration of sin, that is minus cos 2au minus 80 upon 2a, and again limit u equal to 0 to t. This is the integration. Now substitute the lower and upper limit, that is sin 80, upper limit, that is t, lower limit 0. Here minus minus is plus 1 upon 2a. If we use upper limit, put t equal to u equal to t, then sin 280 minus 80, that is cos 80, and lower limit u is 0, so again cos minus 80, right? And you know that cos minus theta is cos theta, so it is plus cos 80, so cos 80 is cancelled out, and finally we get 1 upon 2a sin 80, that is your required inverse Laplace transform, right? Same answer as just I solved this question by previous method, by formula. So similar result I can obtain by using convolution theorem, right? This is the formula, and by using convolution theorem we can find the inverse Laplace transform of some typical type expressions very easily, like that. If you have to find the inverse Laplace transform of s square upon s square plus a square, s square plus b square, you can say this is if you solve this directly, so that will be very lengthy, means you can say that is next to the impossible, but by convolution theorem you can solve very easily, right? I will take another example for to clear convolution theorem, and after that it is the finishing of inverse Laplace transforms. And in next lecture, actually one thing I have to discuss, that is there are some special type of the functions for which you have to calculate the Laplace transform and as well as inverse Laplace transform, and then discuss about the application. Now I will take this example also, again next question, next example, that is you have to find inverse Laplace transform of s square plus a square, s square plus b square, right? This one, and by find this by using convolution theorem. Again, here we have this one, s square plus a square, s square plus b square. So we can separate them as s upon s square plus a square into s square plus b square. Right? Again, take this one as capital Fs, take this one as capital Gs. So here Fs equal to s upon s square plus a square. For inverse Laplace transform small ft is, that is cos 80. Similarly, you are taking Gs as s upon s square plus b square. Similarly, small gt is cos bt by the formula directly of Laplace transform, ft and dt. Right? Now, simply Laplace transform of inverse Laplace, we have to find the inverse Laplace transform of this. So, by convolution theorem, we have inverse Laplace transform of this is equal to integral 0 to t f of u g of t minus u d. Now, substitute the values of small ft and gt into this integral. We get 0 to t, fu means cos au, gt means cos b times t minus u d. Now solve this integral and then you will get your required inverse Laplace transform. To solve this integral, again we multiply by 2 and divided by 2, and now it is a form 2 cos A cos B. And also you know that this formula, that is cos A plus B and plus cos A minus B. Right? By this formula, it will break into two parts, that is cos BT. That is cos, if you open this cos AU, this is BT minus BU. If you A plus B, then we get A minus B into U plus BT. That is the cos A plus B. And when we take the A minus B, that is cos A minus B means A plus B into U and plus BT. A minus B minus BT, right? Because minus, right? That is cos A plus B. A plus B means we are adding AU plus BT minus BU. Combining this. And cos A minus B means AU minus ABT and plus BU. So this one. Right? Now integrate them, and you do that integration of cos is simply sine A minus B U plus BT upon A minus B. And upper limits t u equal to and 0. This is again sine A plus B into U minus BT and upon A plus B and upper limits and lower limit. Right? Now substitute the limit. If we put u equal to t, then from here we get only sine AT upon A minus B. Because when we put t equal to u equal to t, minus bt plus bt cancel out. And when we put the lower limit, in upper limit we get this. If we put the lower limit equal to 0, this one is 0. And then in lower limit, this is sine bt upon A minus B. Right? This is the value when you substitute the lower limit, u equal to 0. In here, in second term, when we substitute the upper limit, then again u equal to bt and bt is cancel out, and finally we get sine AT upon A plus B. When we put lower limit means u is 0, then it becomes 0 minus, and lower limits minus was plus, that is sine bt upon A plus B. Right? This. Then you can combine them, you can manipulate them and find the final results. Some just manipulation, some calculations based on the algebra, that is in the inverse Laplace transform of sine s square a square, s square plus b square, and this is equal to, this is simply in first case, if you take sine AT is common, sine A minus B is common, then this is sine AT. If you take first term and third term, sine AT is common, then 1 upon A minus B plus 1 upon A plus B. In second and fourth term, if you common minus sine BT, then here 1 upon A minus B minus 1 upon A plus B. Like this one. And if you take LCM and calculate them, then from here, this is sine AT, and in numerator we cancel out 2A upon A square minus B square. And here, if you take LCM, then A is cancelled out, and this is 2B A square minus B square. Right? And finally, we get, if we take 1 upon 2, and A square minus B square is common, then and 2 is also common, 2 is cancelled out, that is 1, that is sine A sine AT minus B sine BT. This is your final answer of this inverse Laplace transform, alright, by using the convolution theorem. So by these process, by these methods, you can find the inverse Laplace transformation. If you analyze all the things in this topic and we calculate this, then we get in inverse Laplace transform is nothing different, only you have to use all the standard formula, results, properties of Laplace transform and convert them to get the formula of inverse Laplace transform, and you can solve easily. Okay, now in this I am closing this lecture up to this. In next lecture, first we discuss Laplace and inverse Laplace transform of some unique type of the function, in which two functions in your syllabus, that is unit step functions, and second is unit impulse function. Unit impulse function is also known as direct delta function. And then we come on the last topic of this unit, that is the application of Laplace transform. Okay, thank you.